Very nice. Now we're on. Okay, so this is this next chapter, 14.2. And I'll turn the lights out a little bit so we can see the screen a little better. This section's about origins of life. How did the first life forms get here? And the older scientists and thinkers, a lot of them discuss the possibility of what's called spontaneous generation. Spontaneous generation is the idea that life comes from non-living stuff. And this guy up here, his name's Francisco Redi. He was one of the first scientists to disprove spontaneous generation, to disprove the idea that you can get life from nothing. And I'll show you his experiment. His experiment's the famous meat in a jar experiment. What he did was he took an Erlenmeyer flask, it looks like this, and he put some meat in it. And he took another Erlenmeyer flask that looks like this, and he put some meat in that. And what's the difference between the two? This one has a lid on it, and this one does not. And what ended up happening was, this meat where the lid was on the flask, that meat never grew maggots on it. But this meat that was in the open flask got maggots on it. You know what maggots are? Baby flies. Fly larvae. Baby flies. Because it used to be people say, here's an example of spontaneous generation. If you lay meat on the ground, maggots will come up from it. That's spontaneous generation. Life coming from something that's not living. Living flies coming from dead meat. But that wasn't what it actually was happening, was it? The flies were, the baby flies were coming from other flies that flew in and laid eggs on the meat. And the eggs are microscopic, so you can't see them. And that's how the flies were getting there. So it wasn't spontaneous generation, life coming from lifelessness. Here's another famous experiment that was done by Louis Pasteur. Have you ever heard of Louis Pasteur?
No.
Pasteurized milk, you ever heard of that?
Yeah.
Louis Pasteur made up that process of pasteurizing milk to make it last longer. Because milk will spoil very easily. Milk would only last a day or two. And the milkman used to have to come every day. But with pasteurization, the milk can last for a week or so. It's a process of heating the milk to kill a lot of the microorganisms. So Pasteur worked a lot with microorganisms. And here is his famous swan neck flask experiment. Pasteur knew if you made some broth, which is like soup, it would spoil after a while. Microorganisms would grow in it. But Pasteur didn't know what was causing it to spoil. But it turned out microorganisms were growing in it. But then, so what he did in this experiment was he took some broth in a swan neck flask. This is called a swan neck flask. See the top of the glass here? It looks like a swan's neck. It's curved. And he would boil the broth. And he found out that broth in a swan neck flask would never spoil. No matter how long you left it there, it wouldn't spoil. And now this neck is open to the air, so air can get in. But if with the neck shaped like this, it would never spoil unless you dumped the flask over and let some broth run down the neck to the end of the neck. And if you put it back upright and let the broth come back in, it would spoil. Can you guess what might be happening here? That's correct. What happens when you dump the flask over, see, there are little bacteria that are floating around in the air. They're floating around right now. You just can't see them. One of them landed on my arm just then. And you're breathing them in, actually 5 or 10 of them with every breath. And some of those bacteria will get into the neck of the flask. And they'll settle right here at the bottom. Because they're too heavy to be carried up by the air up this tube. They'll stick to the wall of the tube somewhere. And they don't make it all the way into the flask. Most of them settle right there. And so if you dump the flask over and run the liquid up to the end there, you're going to pick up some of those microorganisms and bring them back to the flask, and they'll spoil the flask. This is another way that spontaneous generation was shown not to exist. It's not like the bacteria come from nowhere. They come from the air. And by the way, one of Pasteur's flasks is in a museum in France. And it's still unspoiled after 130 years.
Are you serious?
Yeah. It's sitting there behind glass with broth in it. Isn't that cool?
So you could eat it.
Yeah. It's 130 years old.
So the same broth he used?
Yeah. It was part of his experiment.
Would it taste the same?
Yeah, it tastes good. You might want to stir it up a little bit. Here's a stupid video about spontaneous generation. Do you like stupid videos?
Mm-hmm.
Yeah.
I thought you would say yes.
This is wonderful. Candlelit dinner in a French restaurant. It's hot. Wine has bouquet. Now the soup. Garçon! Garçon!
Oui, monsieur.
Waiter, there's a fly in my soup.
But of course, monsieur.
Oh, this is an outrage.
Oh, no, monsieur. This is a spontaneous generation.
What?
You know spontaneous generation? The process by which life, our little friend, is produced from non-living matter.
Oh, that's garbage.
No, that's bouillabaisse.
Everyone knows that Louis Pasteur disproved the theory of spontaneous generation over 100 years ago.
Well, if that is the case, then what is that fly doing in your soup?
That's pretty good.
I'm sorry.
You've seen worse.
That's true.
Okay, so if spontaneous generation is not real, that doesn't happen, then how did the first life forms ever get here? Well, one hypothesis is called Oprahs Hypothesis. A Russian scientist named Alexander Oprah suggested that the first living organisms might have come from the gases that were floating around in early Earth's atmosphere. Oprah knew a lot about early Earth's atmosphere. And he knew that it consisted of CO2 and hydrogen gas and some water vapor and nitrogen gas and maybe some ammonia, NH3, and some sulfates. I'll put SOS. These were the gases that were present in early Earth's atmosphere. Oh, some carbon monoxide, too. But Oprah also knew about the chemistry of living things. He knew about organic chemistry. And he knew that living things are made mainly of 6 elements. Do you know what they are? Carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. 99% of organisms' bodies are made of those 6 elements. And Oprah saw that carbon, hydrogen, oxygen, nitrogen, sulfur, they were present in the gases of early Earth. And he knew phosphorus is in the rocks of early Earth. So Oprah wondered if these gases might somehow hit together just randomly in the atmosphere to make a living thing. That was Oprah's hypothesis. And Oprah just guessed that maybe that's what happened, but he never did an experiment to test it. But some scientists came along. Their names were Miller and Urey. And set up an experiment to test Oprahs Hypothesis to see if that could really happen. And this shows their experiment. What they did was they had heated water in this vessel right here. They heated it up with a flame so it would boil. And the water vapor would rise up this tube. And through that valve they put methane and ammonia and hydrogen, these gases of early Earth. They put them through the valve. They knew what gases were on early Earth because they're all trapped in old rocks. If you take a 3 billion old rock and crack it open, the gases that were in the atmosphere back then will come right out. Trapped in the rock. And so if you add those gases that were in early Earth's atmosphere to the water vapor and let them go into a chamber and apply electricity, the electricity is simulated lightning that was present in early Earth. Early Earth was probably a very violent place. A lot of meteorites hitting, a lot of volcanoes going off, very hot place, a lot of lightning striking. And they wanted to simulate that energy, so they put a couple of electrodes there to supply sparks and supply energy. And what that ends up doing to the molecules is exciting them, getting them moving real fast, so they bump into one another. Now, if I throw these two dice together, they don't stick together. They just bounce off one another. It's fun to do, but it doesn't get me anywhere. But if you take two molecules and you slam them together hard enough, they stick together. That's properties that molecules have. Molecules will stick together if they hit one another hard enough and in the right ways. And what they found when they took these gases that were bashing together and then they cooled them off so that they would condense back into liquid, and then at the bottom of the apparatus they could open up the little tube and get some of that liquid out. When they examined that liquid, you know what they found? They found organic molecules. They found little rings of carbon. Do y'all remember what we call a carbon ring? Monosaccharides. They found those. They found lots of monosaccharides. They found lipids, fats. They found lipids that were similar to the lipids that make a cell membrane. They found proteins, chains of amino acids. Actually, they found individual amino acids, single amino acids, but bunches of them, different types. And they found nucleotides. Parts that make up DNA. Just from letting these molecules bash together for a few weeks. And these experiments have been continued and run longer than weeks, run for months and years. They've actually been running experiments like this for 50 and 60 years, ever since they originally did this first experiment. And they've made all sorts of interesting molecules and things inside their test tubes in the lab. There's one of the scientists there. I don't know if that's Miller or Urey staring at his little contraption. They got a Nobel Prize for doing that. So the early Earth must have looked like this. It must have had simple gases floating around. And a lot of lightning and energy. And those gases, just like in the experiment, must have bumped into each other and likely formed simple organic molecules like amino acids, glucose, fatty acids, purines and pyrimidines, the nucleotides that make up DNA, formed from these collisions and fell down into the ocean. And the ocean was called, the scientists like to call the ocean, the ancient oceans of the world, call them organic soup. Or you may have heard the statement primordial soup. Have you ever heard that?
I've not.
That's what scientists call the early oceans. an organic soup or a primordial soup. It's just a bunch of organic molecules in the water. And by the way, the word soup, that's exactly what this is. Do you know why I said to take a spoon back with you if you go back in time? Because you could have dipped it in the ocean and ate the ocean. It would have tasted like soup. It would have had lots, millions, trillions of these molecules in it. Glucose is sugar. Fat. That's what's in soup. Salt from the erosion of the rock. It would have tasted like soup. The oceans, well, you could eat the oceans back then. Isn't that interesting? It's very different from the way it is now. You can't eat the oceans now, you get sick. A bunch of salt water. But back then it had glucose in it. And fatty acids, the same thing that's in like soup that you buy in the store. Here's something else that scientists noticed. Y'all know what clay is? Clay are like particles like baseball players. We got baseball players in here? So you guys know you get clay on your shoes, the red stuff that they make in the baseball diamond. Those little clay particles have a certain charge to them that attracts amino acids. Amino acids will stick to the clay particles. And that's what they show here. When you do these kind of experiments like Miller and Urey did, and you add some clay particles, the amino acids will stick to the clay particles. And then, if you dry out the clay particles a little bit, and you apply some sunlight, the amino acids will bond together and make a chain of amino acids. You know what we call a chain of amino acids? Proteins. Proteins had to have been forming on early Earth, on the sand particles next to the oceans. Like that. On the clay particles that were on the rocks next to the ocean. So, you could form proteins. And it's been shown to happen in these experiments they've done. So they've let these experiments run for years and years and years. And in the lab, they form these balls of protein they call proteinoids. And they form these balls of fats they call liposomes. And those are starting to look a lot like cells. And it's just from letting these experiments run, like Miller and Urey's experiment, letting them run for years and years and years. And they've even formed in the lab special cells that they call protocells. See that word there, protocell? That's a protocell. It's a collection of a bunch of a membrane. These protocells have a membrane, and they pull in organic matter, comes in and builds up inside the membrane just like in a cell. And these things grow with time. They get bigger and bigger. And you know what happens when they get real big? They divide in two, just like a modern cell does. And all of that has been made in the lab. These protocells behave very similar to real cells. And so there's a lot of advancement in this field, and they're getting close to having getting an actual cell to form, starting from scratch. And I think that'll happen in our lifetimes. They're saying it's maybe 10 years away. But I like to be pessimistic a little bit because maybe 30, 40 years down the road. Maybe 10 years, but it won't be interesting. That will be, if they ever get a cell that forms in a test tube that's living and can grow and multiply on its own, that will be the first living thing that's formed ever since the first living things on the earth. That will be an amazing, amazing achievement. Something that we haven't seen yet. So, here is kind of a chart, and this isn't from your book, it's from the AP Bio book, but it kind of shows that early Earth had these simple molecules which come together to make more complicated molecules. And we call this, going from simple molecules to more complicated molecules, we call it chemical evolution. And then those complicated molecules might come together over time to form protocells. They've actually got protocells to form. And they think that the protocells, given enough time, could become cells if you continue letting them take in materials, letting materials stick together. They think maybe they could form cells that way. And we call that biological evolution. Now, it's never happened. They've never actually formed a cell. And even if they do form a cell this way, it doesn't prove that that's the way it happened on early Earth. But it is suggestive that maybe that could happen on early Earth, which is very interesting to me. You want to see what it must have been like on early Earth? Kind of a cool video to show.
Planet Earth at the beginning, 4.6 billion years ago. Its surface erupted in a sea of molten magma. A billion years later, the planet was in the midst of a slow cooling process. Vapor rose to the sky, condensed, and fell to Earth in a torrential downpour. In the aftermath of the seemingly endless deluge, the primordial ocean was formed. The atmosphere after the formation of the ocean was heavy with carbon dioxide, much like the planet Venus today. Earth was sealed off by thick clouds, and the lonely streaks of sunlight that penetrated the cloud mass tinted the sky orange. Earth was like a giant steam bath with ocean temperatures soaring over 300 degrees Fahrenheit. But in this primordial soup, the building blocks of life were accumulating. Meteorites showered the earth, perhaps bringing amino acids necessary for the formation of life. And then one day, 4.5 billion years ago, an asteroid the size of Mars collided head-on with Earth. This giant impact was the greatest event in our planet's early history. The impact was of such phenomenal magnitude that it carved out part of the Earth's mantle and hurled it into outer space. A portion of the torn mantle was drawn back to Earth. The fragments of debris scattered into space were swept up by powerful gravitational forces. They formed a new satellite, which would eventually circle the Earth. This was the birth of the moon. The giant impact shook the Earth to its core, new molecules. Some, such as hydrogen cyanide, would have been lethal to humans. Tiny molecules of these toxic compounds combine to form larger ones. Out of this mix, other molecules that would eventually form DNA, the blueprint of a living cell, took shape. This first step toward life would take nearly 1 billion years to complete. Eons later, no one can explain how the graceful double helix formed, transforming inanimate compounds into living cells, cells that can grow and reproduce. The catalyst of life remains unknown.
Cool. Is that a good video?
Not bad.
It talks about after you have the first cells, cells eventually start living together, start living with one another. And we call a bunch of prokaryotic cells that live together a eukaryotic cell. And that idea is called endosymbiosis. Endosymbiosis. Y'all heard of chloroplasts and mitochondrions? Y'all remember that from when we studied cells? Chloroplasts and mitochondria were once free-living cells, and now they live inside of the eukaryotic cell. A eukaryotic cell is a collection of several cells all living together. It's called endosymbiosis. And it took about 2 billion years for the eukaryotic cell to evolve. So this is all interesting stuff about how life formed and got to be as complex as it is now. You need to read 14.2. That's your homework, okay? Great job, John. Way to go. Y'all have a good one.